the disk. If we look at that closely, you can see that one sees the diameter here, and this edge has to be exactly parallel to the diameter, and the circle of the glass has to be concentric with the axle of the disk, and one can see a circle guideline here which helps one set that up so that the space between the glass and the circle is absolutely uniform. Having done that, then one must adjust the light so that it comes in and shows clearly, and that we can't see with the cameras unless we turn some of the studio lights off. So let's do that, and then we can see the light coming in. It's not quite adjusted now, and by tipping the plane of this thing, one can have it so that it comes clear across the disc and shows coming in here and shows going out. But it's also important that it come in exactly along a diameter, and that it's not now doing. For example, although it's coming in at 0, it leaves that. By tipping the light, I can get the adjustment, and also by raising and lowering the light. So a combination of tipping and raising and lowering enables me to adjust it so that when the light comes in at 0, it goes along a diameter and comes out exactly at 0 over there. I can finally check the adjustments by allowing the light to come in, say, at exactly 20 degrees, and then measuring where it comes in. It's not quite clear there. I have to adjust the plane a little bit, and measuring exactly where the refracted ray goes, and then I can go to exactly 20 degrees on the other side, set the 20 degrees right in the middle of the light beam, and read again here where it goes, and those should agree, hopefully within half a degree. If not, one can readjust either the prism or the way the light comes in, so that you can see which one was not quite right. In general, though, it's best always to make measurements on both sides. One can study the effects here and see where the total internal reflection comes in, and then one can make similar measurements, allowing the light to come in along the plane face and looking at the angle of refraction as it comes here on both sides of the normal. In this way, one can plot the angle of incidence against the angle of refraction over a wide range and see how well Snell's law is obeyed. It's also possible, especially under conditions such as this, where you get total internal reflection, to see the difference in the colors. If one places down here along the bottom edge a white card, you can see the colors due to the dispersion of the glass, and see that the total internal reflection occurs for one color before it occurs from the other, and see what the difference in angle is, and in that way measure the index of refraction for two different colors. That's all that's involved here, but to get accurate results, one does have to be very careful of that the initial settings are well done.
Experiments in Physics with Dr. Frank Oppenheimer was produced in cooperation with University of Colorado Television. This is University of Colorado Television. Experiments in Physics with Dr. Frank Oppenheimer. A brief demonstration of the equipment used in the Library of Experiments in Physics, produced in cooperation with University of Colorado Television. Today's experiment.
This is a very simple experiment in which one can verify Snell's law and examine it, but one first has to make some adjustments fairly carefully. What one uses is an optical disc with a semicircular piece of glass at the center and a light shining through, and one simply observes the path of the light. The optical disc has a slit in it, which one can see here. There are several slits, and one of them is covered up. And then on the back of the disc is a handle which can be turned, which rotates the disc. So one can have the light coming in and hitting at various angles. But before doing anything else, one has to get very careful adjustments of